Hello everyone. Generative AI is going to revolutionize the way that we work. Or is it? Well, the answer depends on how you implement it. The reality is, according to McKinsey, 90% of Gen AI pilots fail to move into production. Now, why is that? Obviously, for a complex problem like that, there are a lot of reasons. But a large part of it is that the way you manage your data platform matters a lot. If it's not set up for success, the chances of making your Gen AI project successful go down significantly. Not having a single version of the truth, having data sources siloed from each other, not being able to marry structured with unstructured data, not enforcing data quality, the list goes on and on. What this means is that data analytics are critical to getting your Gen AI workloads deployed successfully. My name is Ismail, and today, with my colleague Lydia, we'd like to welcome you to this session on best practices for analytics and generative AI in AWS. Today, hopefully, we're going to be showing you a practical approach for how you can combine analytics services and best practices for operating those analytics services on AWS with your Gen AI workloads to turn your Gen AI vision into a reality and hopefully become part of that 10% that moves their Gen AI pilots into production. So, the session today is broken up into three parts. First, we're going to be talking about some basic concepts relevant to generative AI that will give us some context for the rest of the discussion. Then we're going to be walking through a quick demo, which is going to be a Gen AI-powered bot. From that demo, we're going to have a reference architecture. That reference architecture has a combination of analytics and Gen AI services, and they're going to form the rest of our best practices discussion. Each of the subcomponents in our architecture, we're going to dive a bit deeper into. They will have analytics services within each subcomponent, and we'll talk about the best practices for those analytics services. So, let's start with the basics. I'm sure everybody in this room knows what generative AI is, but some definitions would be useful here. So generative AI is a class of artificial intelligence in which you take some inputs, you train a model, and you output content. That content could be text, could be image, could be audio. This is different from classical machine learning, which usually outputs a deterministic result, like a prediction, like a binary classification, or something like a score, for example, but not actual free-form content, which is what Gen AI produces. Another unique feature of Gen AI is the vast amounts of training data that is used to power it. And that training data is unsupervised and it's unlabeled. Now, the engine that powers Gen AI are called foundation models. These form the basis of the predictions or the content that will be produced in the future. A subset of foundation models is the large language model, which is basically a foundation model for text or language use cases. Now, what can Gen AI be used for? Now, of course, I'm sure you're all famous with the virtual assistant use case. It's the way that many of us got introduced to Gen AI. But there are many other use cases like text generation, for example. So if you wanted to produce a new poem in the language of Shakespeare, you could train a Gen AI model with The Merchant of Venice and Romeo and Juliet and have a new poem spoken like Shakespeare, for example. You can also summarize existing text. You can also search for text. You can also search across the vast amounts of data that the foundation model is trained on to synthesize information into easy-to-consume bullet points. You can use it to augment code. You can use it to generate new images. The list goes on and on. So, a lot of organizations want to actually implement these use cases and they want to build them out. There are some difficulties with building out Gen AI applications, so we're going to guide you through some patterns that we see across the organizations that we work with so that you can select the pattern that fits your use case. Now, there are three patterns we're going to be talking about, and we're going to assess them across two dimensions. The first dimension is adoption. How easy or complex is it to adopt this way of building a generative AI application? The second dimension is grounding. And what grounding means is connecting the output of the model to verifiable data to stop the generative AI model from hallucinating. So it's basically grounding the model in truth. So the first way is to train your own model from scratch. And you can train your own model from scratch and train it on your custom data. This is useful for very domain-specific use cases. So for example, Bloomberg has built an LLM called Bloomberg GPT specifically for financial services. Another approach is to take a pre-trained model and fine-tune it with your data set. So the model already exists, but you're using your specific data set to tweak it or tailor it to your specific use case. The third way, which is the easiest to adopt, is to use in-context learning. Now here we don't change anything to do with the model parameters or the training data set. Instead, we feed the model context, and that context refines the output from the model. So what do we mean when we say context? Well, there are two types of context here. Situational context, which is the conversation state and history. Usually that's fed to the model with something called prompt engineering. And the other type of context is called semantic context. So that is relevant data that exists, let's say, in your enterprise data stores that are not part of the training data set. So you have the actual prompt and you go retrieve data from your enterprise data stores and you send it back to the generative AI application to augment your prompt. That is referred to as RAG, or retrieval augmented generation. That's one of the famous techniques for producing semantic context. So these are the two types of context that are used to produce similar results without having to train your own model or tune an existing model. So the demo that we're going to be talking about is going to be using that third approach, in-context learning. So what does that actually look like? So first we have a user, and the user sends a prompt to the model. Keywords are extracted from that prompt, and they are sent to an enterprise data warehouse and a data lake, where we have tabular information, which is going to provide part of our semantic context. Now, we could also have files, documents, free-form types of data that are not captured in our data warehouse or data lake efficiently that we can also use to train the model. Now, those documents need to be captured in some kind of way that the model can make sense of. So they must be turned into a numerical representation first. That process is called vectorization. And so those files and those documents are stored in a vector database as vector embeddings, which we'll talk about in a second. Now, that semantic context is then taken back, run through the large language model, and it's used to augment the original prompt. So now we have an augmented prompt that has the semantic context from our data warehouse, data lake, and our vector database. That's run through the LLM, and now we can have much richer context. We can have a response that is based on much richer context sent back to the user. So what are vector embeddings exactly? So as I mentioned, there are a numerical representation of files, documents, unstructured text, etc. Let's take the example you see here on the slide. We have some insurance documents here on the left. We extract keywords from them, so collision coverage, policy premium, etc. We break basically the documents up into chunks. That process is called tokenization. And then we convert those tokens into vectors. Vectors are just arrays of numbers, which you remember from math class in school. But what's special about vector embedding specifically is that these numerical representations here, they preserve the meaning, the original meaning that comes from the document, and the relationships between different elements and each other. Now, this is important because these vectors get projected onto a multidimensional space. Here on the right, we have a 2D representation of that space where you can see different concepts that are linguistically separate, so they're not written like each other, but conceptually they are similar. So when we are searching for meaning within our vector database, we can find different elements that have meanings relevant to each other, which is very powerful in the context of an LLM model. So using all of these concepts, we're going to run through a quick demo. This demo is a GenAI-powered bot where you feed it context about an employee that wants to get promoted, and the bot is supposed to produce a body of work for that employee. Now, you can see the prompt is quite large because we have the prompt itself in the situational context fed directly into the question. But in the back end, we have this employee's KPIs, their performance metrics, their activities, their customer satisfaction scores in the enterprise data warehouse and the data lake. We've also added role leveling guidelines, other promotion documents, expectations from the company, their values and leadership principles in the vector database. So from there, we've grabbed the domain and the semantic context and the situational context from the prompt up here, and we've produced this rich result. So what does this demo look like from an architectural perspective? Let's walk through what this architecture actually looks like and what the components are. So first, we have the user sending a prompt to the generative AI application. The application pings the conversation history, which is stored in a NoSQL database. And then the the Gen AI application sends the keywords to the data warehouse and the data lake for additional domain context. So what happens here is we use a Lambda function to grab metadata from Glue Data Catalog and use it to form a SQL query, which is sent to Redshift, which passes back that context that we talked about, where we have the activities and the performance metrics of the employee. We also mentioned that we have files and documents where we have role guidelines and leadership principles. Those are ingested through a streaming layer, landed in the data lake, run through the LLM, and vectorized, and that vector engine is stored on the Amazon OpenSearch service, which is then also sent to the generative AI application. Now that we have all of this extra context, we can augment the prompt, and now we have a richer prompt that has the context from our enterprise data warehouse, data lake,
sessions have now finished.
And the vector
Drinks
database.
served in the Partner Expo area.
Together, those produce an augmented prompt, which is sent to the LLM, which is then sent back to the application. The conversation state is updated, and finally, we send a rich result back to the user. Now, do you need every single component here to implement something like this in your organization? The short answer is no. The long answer, as usual, is it depends. But the point of this architecture is for it to be a reference architecture. You can take each of these subcomponents and switch it out with whatever makes sense for your organization. There are some overlap between these services here, but we want to give you a superset of the different services and what they can do to fulfill that functional part of the architecture. But you can adjust and tweak and change based on your specific IT environment and your application needs. So now we're going to use this architecture to dive into each of the subcomponents and talk about best practices for the analytics services within. But before we do that, we want to talk about some design tenets which are going to form the basis on which we're going to optimize for these analytics services. So when we build out these different services and when we think about architecting them, we want to have 4 design tenets in mind. The first is simplicity. We want to minimize the amount of code we want to write if it's not necessary, and we want to minimize the amount of data copying and replace it with data sharing instead, so that we don't have lots of different forks of the data, and minimize the amount of error happening on analyzing the same data set but in different silos. The second thing we want to optimize is flexibility. We want the different parts of our architecture and the components within to be modular and incremental, so that we have separation of concerns from an architectural perspective. One of the most famous or common, let's say, implementations of this is decoupling our storage from our compute, which is a common trend in analytics these days. You want to be able to scale them out separately, which brings us to our third design tenet. Your workload patterns and your usage patterns are going to have different demands on different parts or different components of your architecture. So being able to scale out or scale in or scale up or scale down each part of the architecture is critical. Being able to use different frameworks, different tools, and different programming languages are also a critical component of scalability, which will help you to maximize the robustness of the architecture that you produce. And finally, last but not least, reliability. Your data pipelines need to be able to detect errors. You need to be able to troubleshoot them. You need to be able to log and monitor so that you can maximize your operational excellence and deploy your analytics pipelines into production. So we talked about the Gen AI workflow, which flows on this slide from left to right. But when we talk about the data pipeline workflow, we're going to go from right to left. So the first thing that we need to do, just like in any data pipeline architecture, is actually ingest the data. So we have different diverse data sources here on the right. We're going to ingest them through a set of streaming services. Now, those streaming services are going to then update the conversation state, which is going to update the situational context for the GenAI application. However, the data is also going to be sent to the data lake for further processing. On one side, you can process it for analytics and send the data to the enterprise data warehouse and the other parts of the data lake, but also to be able to send the data to your vector database to be vectorized and provide the semantic context for your GenAI application. So let's talk about some of the streaming services that we have on AWS. So here we have Amazon managed streaming for Apache Kafka, or Amazon MSK for short. This is a managed version of open source Kafka, which is commonly used for as a message broker for event-driven applications, or in this context, for streaming storage for ingesting streaming data and messages. So it's fully compatible with open source Kafka, and it's also used to manage Kafka Connect clusters as well. Now, if you're not using Kafka already, or you don't need it for your use case, and you want to lower the learning curve for ingesting streaming data, you can use Kinesis Data Streams, which is a scalable serverless Amazon solution for streaming storage. Now, both MSK and KDS serve a similar function in this architecture in that they are streaming storage solutions. But what about actually processing that streaming data on the fly? That's what we would use Amazon managed service for Apache Flink for. Now, Flink, like Kafka, is open source, and we have a managed version of Flink, which is used for unified batch and streaming. It's used for interactive analysis. You can write streaming applications on Java and Scala, which will benefit from features like windowing functions and time-based functions to analyze sliding windows of your data on the fly and being able to produce insights in real time or near real time. So for the remainder of our discussion today, we're going to be talking about best practices for each of these services. Now, if you don't capture everything we're about to say, not to worry. We have a QR code here at the bottom of the slide, which you can scan so that you can have a reference to the documentation or blog post, which is the source for the best practices we're going to be talking about. And then at the end of the session, we're going to have a slide with all of the QR codes in case you missed any of them in the middle. So if you're operating MSK, what are some of the best practices? Number one is to regulate your broker CPU usage. You want to give some headroom for your operational for fault tolerance, and let's say you have a change like a version upgrade or a broker fault. You want to keep your CPU utilization at around 60%. Now, if you want to mitigate downtime and throttling issues, you should also manage your throughput limits. You want to cap it at around 80%. Now, if your application is very storage greedy, you're going to want to benefit also from the storage autoscaling feature, which MSK uses for dynamic growth. However, it's also important for you to be able to rightsize your cluster as your application needs change. So looking at your latency, your availability, and your throughput needs will determine your calculation for the number of brokers and partitions you need if you're using MSK in provision mode. Now, if you're using KDS, there's a different set of optimizations you want to look at. Now, KDS in general is built, and the billing is a function of the message size and the number of messages. So if you want to optimize this, you're going to want to aggregate and compress your messages. A simpler way to do that is to use the Kinesis producer libraries and Kinesis consumer libraries, which will abstract some of that operational complexity away from you. And you can use the KPI, you can use the enhanced fan-out with parallelism feature in KDS, so you can have dedicated throughput for each of the streams themselves, up to 2 megabytes per second of throughput. The last consideration for Kinesis data streams in this talk is to look at on-demand versus provision. Usually, on-demand is useful if your traffic or the requirements for your application are unknown and they're spiky and they're unpredictable, and provisioned if you have a consistent and predictable workload pattern, I should say, or if your capacity requirements for your throughput are not being met by the on-demand mode. So those are the recommendations for streaming storage. Now, when it comes to streaming analytics with Apache Flink, it really is a function of the performance of your application itself. So the first recommendation here is to enable checkpointing. Checkpointing is important for fault tolerance. The second is to manage your snapshots diligently. Now, snapshots are useful to maintain your application state and restore it when needed. And of course, this is very useful when it comes to deploying your applications in production. However, there is a cost and performance trade-off, so you want to see if that trade-off is worth it for your pre-prod and development environments. Last thing to mention about MSF is operator parallelism. So Flink operators can help you transform data streams into new data streams, and through multiple transformations, you can transform them into complex data flows. Now, the parallelism is usually set at the application level by default. However, this can cause some provisioning issues at the data source and the data sink. So you're going to want to make sure that you set your operator parallelism as a function of the application or the function of the data source, depending on your needs. So going back to our demo architecture here, we talked about ingesting data through streaming services, and we talked about the best practices for those streaming services. We land that data into the data lake, and then we want to vectorize that data and sync it into a vector database on Amazon OpenSearch service. So Lydia is going to be walking us through the Amazon OpenSearch service and the best practices for it, as well as the best practices for the rest of the architecture in the reference architecture here on the slide. Thank you for listening.
Thank you, Ismail. Now, let's unpack the rest of the architecture. Start with Amazon OpenSearch. Amazon OpenSearch is a fully managed distributed database that enables your search and log analytics use cases. In the demo architecture, we consider Amazon OpenSearch to centralize logs from application server and from AWS services for operational analytics. In OpenSearch, data must be in JSON format. Then we send the data into OpenSearch domain where it is indexed and made available for query. In the consumption side, you can have your application query for a search result or for near real-time monitoring, dashboarding, alerting for your log analytics. To make your OpenSearch workload fast and efficient, there are some factors that come into play. So sit tight, I'm going to tell you all about this. Start from the basic. Data in OpenSearch stored in an index, similar like a database tables. Index composed of multiple shards. So when you create an index, you can choose the number of primary shards. Then the data will be distributed across those primary shards. You can also decide if you want to have a replica shard, which is a complete copy of your primary shards. Then shard will be distributed across the node to enable parallel processing. In OpenSearch, shard is very important because the shard is your worker that maps to a CPU. So here are some best practices for your shard strategy for Amazon OpenSearch. First, consider the size of your shard based on the use cases. For search use case, where the amount of data reads and the performance important, aim between 10 to 30 gigabytes. For log analytics, where it involves heavy writing, aim for 30 to 50 gigabytes. Then consider the number of shard count per node based on the memory size. Aim maximum 25 shards per node and allocate 1.5 vCPU per active shard. Then distribute the shard across the node to enable parallel processing. Particularly for streaming use case or log analytics, you're typically going to receive a huge amount of data in daily basis. The nature of data is the most recent data, you want to query that often in the fast performance, while the older data you query less often and you don't need as fast performance. So how are you going to deal with that? You deal with index state management. This feature allows you to set rules to move your index from hot tier to the ultra warm tier when your index gets old or your document size hits certain limit. So the new data will be stored in the hot tier, which is backed by EBS that give you high performance, high throughput. And then when the condition met, index is moved to ultra warm tier, which is backed by Amazon S3. As you see here, you trading between performance and cost saving. Eventually, you archive the data in the cold tier and then delete it. This feature automates the migrations and the deletion of index. So now let's summarize best practices of using Amazon OpenSearch, especially when configuring your instance type for your hot tier. You should choose Graviton to instance type and GP3 EBS type for better price performance. Use reserved instance for additional cost saving. Now we can continue building our data pipeline. We're going to talk about Amazon S3, your object storage. To make sure your analytics run faster against data in Amazon S3, you must well organize your data. And how are you going to do that? You do that by partitioning your data based on the filter that you use the most. For example, a dates column. Then store the data in columnar format like ORC or Parquet so you can scan less data. Compress the data in such a way so you can split it up so you can process parts in parallel. And finally, make sure the file size is not too large, it's not too small, and between 128 to 512 megabytes. All of this is important because when you query data against data in S3, you want to be able to scan less data, use less I/O operation, and make everything run faster. Now we have our data in Amazon S3. The next step will be clean up the data, check the quality, and transform the data. And to do that, we're going to talk about two services, AWS Glue and Amazon EMR. Start with AWS Glue, an end-to-end serverless data integration service. When setting up your data integration, you must connect your data sources and the destination. AWS Glue provides many connectors to do this, or you can use connectors from AWS Marketplace, or you can even build your own custom connectors on AWS Glue. AWS Glue runs on top of open source engine, and it has the capability to catalog your data and check the quality of your data. For developers, AWS Glue provides visual code editor called Glue Studio, so you can just drag and drop the component to build your data pipeline. But if you prefer to write your own code, you can use Glue Studio Notebook. Glue Studio Notebook now integrates with Code Whisperer. So your developer, instead of writing the code directly, can use plain English to write the code. Let's see the example here. This is the PySpark code. We want to transform JSON to data frame and store in Redshift. What you need to do is just to write in a simple, plain English. Code Whisperer generate the codes for you. Let's move on. AWS Glue, like any data integration service, provide capability to monitor and schedule your workload. AWS Glue engine support Python shell that runs in a single node, but if you need distributed support, you can run in Ray or Spark engine. When you create your Spark job, you can select different worker type that meets your performance need. And when you execute the job, you can choose standard execution mode or flexible execution mode. With flexible execution mode, you can save up costs because essentially you use spare capacity for your execution. But remember, only use flexible execution mode for a non-time sensitive workload. Now, let's summarize best practices of using AWS Glue. When you select your worker type, make sure you drive from your performance need and SLA. Enable auto-scaling so Glue can scale out and in based on your workload. Set job times out. By default, it's 48 hours. You can always adjust it as you need. And then turn on monitoring so you can always monitor your performance and make that necessary adjustment. For incremental data processing, use job bookmarks. For the Spark application itself, to make sure the performance is improved and use less I/O operations, use predicate pushdown and filter out the table before you do table joins so you can minimize the data that will be processed. Now let's talk about big data processing, and this is where EMR comes to the picture. EMR support various open source framework from Spark, Flink, Trino, HBase, and so on. In EMR, there are several deployment options. EMR on EC2 gives you full control of the type of instance and the numbers of instances you need. It supports a wide variety of open source framework. If you're running Spark application on EKS, EMR also supported on EKS to run Spark application. EMR serverless simplifies all the management and experience setting up EMR cluster. It is primarily support Apache Spark and Apache Hive. If you need your EMR cluster to be closer to your premises, EMR also supported on AWS Outposts. When you create EMR cluster, there are two options. The first one is uniform instance group, which you create or you choose a single type of instance, either on demand or spot pricings. This option is good if you are new to EMR or you have specific workload that require a steady amount of resources. The other option is instance fleet, which you can create spot, you can create core instance, core and task node by combining the spot instance and on-demand instance. This is good for a complex EMR workload, allow you to adjust whatever you need for between performance and also cost saving. Task node do not store data, so it is a good idea to use spot instance. If the spot instance gets interrupted, EMR will automatically replace it, and Spark on EMR can handle it gracefully. So it can save you costs and also increase your computing power. For unpredictable workload, managed scaling on EMR will automatically add and remove resources as per your workload. You just need to set the minimum and the maximum limit. EMR will handle the rest. EMR file server. EMR file system allow EMR interact directly with Amazon S3. So now you can store your data in S3 separate from your compute cluster. So if you have a big EMR cluster run a lot of different tasks, for example, batch processing, now you can have EMR grab the data from the storage, do something about the data, store it back, and then you can shut down the cluster. It means instead of having one big EMR cluster, you can have multiple EMR cluster, each tailored to specific workload to specific size that give you further cost saving. Now let's summarize best practices of Amazon EMR. You should choose instance based on your workload need, based on the SLA that you need. Consider graphing to instance to save costs, and also set up managed scaling for unpredictable workload. Take advantage of EC2 saving plan and reserve instance for further cost saving, and once again monitor your workload, make adjustments when necessary. Now we have our curated data with appropriate quality. The next step is to do the analysis using Amazon Redshift, and we're going to have multiple different data warehouse to leverage Redshift data sharing. Amazon Redshift, it is a fully managed data warehouse with massive parallel processing, purposely built for large-scale analytics. In Amazon Redshift, you can access data directly from Amazon S3, your data lake. It means you can have single query both data in your data warehouse and in your data lake. You can get data from multiple sources. Could be batch, could be streaming. Redshift can handle streaming of data and works well with Amazon MSK and Kinesis data stream. Redshift can connect with your operational data warehouse, such as RDS or Aurora. So you can use federated query to query data from Redshift directly to your data in operational databases. And with zero ETL, data changes in your Aurora cluster can be replicated instantly to Redshift without you have to build a complex data pipeline. Zero ETL, currently available for Aurora MySQL, soon will be available for RDS MySQL, Aurora PostgreSQL, and DynamoDB. In the consumption side, you can have any BI tool of your choice to connect to Redshift. Redshift also integrates with SageMaker, so now you can run your machine learning model directly on Redshift with simple SQL command. And recently, Redshift offers preview feature that allow you to build machine learning model based on large language model that is available in SageMaker Jumpstart. Redshift separate compute and storage. This enables you to share data across data warehouse in single AWS account, or across AWS account, or even across AWS region. This enables you to implement multiple architecture patterns, including hub and spoke, as well as data mesh architecture. So let's summarize best practice for Amazon Redshift. Use RA3 or serverless configuration to separate your compute and storage. When you size your data warehouse, make sure it is based on the size of your data and how you're going to consume your data. Use data sharing to isolate your producer cluster and the consumer cluster. For Redshift provision, use AutoWLM for unpredictable workload, and then set query monitoring rule to control your data traffic. Use concurrency scaling for spiky workload, and use reserve instance to save costs. And serverless, set maximum limit of your RPU to control your costs. Now, the most important part of using generative AI or having data analytics pipeline is to centralize governance and enforce access control. Here, lake formation comes to picture. AWS Lake Formation provide a centralized governance and also granular access control. With Lake Formation permission model, you can use either database style permission or tag-based access control. Both integrate natively with other services. I'm going to slightly dive into tag-based access control. So with tag-based access control, I'm going to explain in the example. We create permission by creating a tag. So in here, we're going to create a permissions using tag to classify data sensitivity. We start by creating the tag itself, and then we apply the permission to a database where all the table underneath will inherit the permissions, but you can override it individually in the table level or column level. Then you can assign the tags to the principals. The best practice is to use tag-based access control. And I'm going to tell you with the example why this is the best practice. Suppose you have 4 individual and 4 resources. With database style permission, you have to create 16 permissions. If you have the 5th resources, you have to add another 4. So in total 20. With tag-based access control, so you create the tag and then you assign both to the resources and also the individual. The permission will be applied automatically. When you have the 5th resources, you just need to assign the existing tag. So with the lake formation access control, now you can enable data sharing securely that allow you to implement various architecture patterns, hub and spoke, data mesh, or even business-to-business architecture pattern. Once again, your data is your key differentiator for generative AI. Generative AI not only required a traditional best practice on analytics, but also highlights some areas that previously overlooked, such as vector database. This is not a new technology, but generative AI made it mainstream in the context of semantic search. Unstructured data. We know unstructured data has long surpassed structured data, but generative AI highlight the needs of handling unstructured data as careful as structured data. Generative AI serves wide range of users. Combined with the unstructured data, it increased the need of privacy, compliance, and security. Generative AI emphasizes the importance of data quality and data strategy to unify data, breaks down silos, enhance discovery, cataloging, and governance. So to wrap up, all information that we shared today is the guide for you to build a solid foundation for your generative AI and data analytics platform, all based on the 4 key tenets: the simplicity, flexibility, scalability, and reliability. Now, I'm going to pause here. You can take picture of this slide. This is all QR code that we referenced before. It's referred to the blog post written by our specialists. It gets updated when information changes, so it's worth to take the picture. All right, Ismail and I really appreciate you attend the sessions. If you could fill out the survey, that would be amazing. Thank you all so much. Now you can relax and enjoy the drinks. Thank you.